Hi, everybody, and welcome back. So, we had just gone over or just reviewed the foundation of logical subsetting, the process, and I'll go back through the process again. But the idea is we want to extract a column from our tibble and then perform some sort. So, this is a column that we would like to use as I guess a good phrase would be like a gate or a control to see which rows of that tibble we want to retain. So an example would be that we had talked about last time was like males between the ages of 18 and 35. So you would need the column for the sex assigned at birth, and you would also need the age column. So you need to pull these two columns out of the tibble and then build a sentence, like a logical sentence of logical comparison operators on the values of these two columns that you pulled out of the data set. And what that will result in is it doesn't matter how many logical steps you chain together, you will eventually end up with one column that's just trues and falses equal to or with the same dimension as the number of rows of the tibble. And that'll basically be like if I have an Excel spreadsheet with 20,000, 50,000 rows or something, then I'm going to end up with a single column with 20 to 50,000 trues and falses. And that will allow me to say, okay, now just show me the records from this data set where these values are true. Okay. So that's basically the idea of what we're going to go through. But here's an example of it. So if we want to say we want to see which superheroes were in print, comic book superheroes that were in print prior to the U.S. involvement in World War II, and so we're going to use a numeric. We first need to find out, well, when were they printed? Okay, so that's step one. Go into this data set and pull out the column that says when were these first printed. And so that's a column called first run. And so this is the data set. So if you remember, there's 5 rows in this tibble. And so we have a vector here. This is an atomic vector with 5 entries: 1941, 1940, 1962, 1939, 1938. And then we say, okay, well, we know that for the United States, World War I started. Let's see, the Empire of Japan bombed Pearl Harbor December 7th, 1941, I think. So basically, let's just say anything less than or equal to 1941, because December 7th is basically the end of the year. So anything, this is so first step one, this is extract this column that says when the first issue of this superhero was printed. And then in step two, compare this using logical comparisons to create a vector of trues and falses. So now I have a vector. There are 5 rows here, and I have 5 logical values of trues and falses. So true, true, false, true, true. Then step 3, apply this vector of trues and falses to the original tibble of data and say, give me only the rows where this is true. In this case, it's going to say, give me the first, second, fourth, and fifth row. And that's how we do this. So we say, okay, well, here's our step 1. This is extracting the column out of the data set. That's the first run. Then step 2, the logical comparison operator for the rows. And then step 3, notice that we're on the left-hand side of the comma, which means we're applying trues and falses to the 5 rows of the data set. And we subset. That's this step right here. We subset out from this tibble only the rows where the first print run was 1941 or earlier. And notice here, we've cut out basically everybody except for Spider-Man, because Spider-Man didn't start, they started in 1962, okay? So again, this character relationships, as I mentioned here, there's a lot more detail in the stringer lesson, which is down here, this wrangling character strings with stringer. But regardless, this again just will give me a vector of trues and falses. This isn't the same like traditional logical comparison operator that we had seen before, like the equal to or not equal to or less than or greater than or something like that. Instead, it's going to be using these string detection functions, but it will return again a logical comparison operator. So a single logical vector of length 5, because I have 5 rows in the data set. And so I say I want to find every superhero that has the word man in it. And then I'm going to extract. I'm going to keep the rows. Again, notice we're on the left-hand side of the comma here. I'm going to keep the rows where this is true. And so we get Wonder Woman. So there's MAN and Wonder Woman, Batman, and Superman. Notice we miss Green Lantern. And then here are some exercises here. And one of the exercises is, why don't we find Spider-Man? So we're looking for man. Why don't we get Spider-Man? So I'm going to pause the video here. I want you to work through these exercises, and then we'll come back and we'll see if we can apply something similar to this, or at least the relational subsetting or just subsetting in general to lists. So we'll be back shortly, but take a minute and work on these exercises. Okay, so we're back. You had some time to work on these exercises, and now we're going to move on to lists. So one-dimensional atomic vectors, this collection, this strand of information, the rules are a bit different, and simply because, and the reason for this is the str detect, the infix in operator, and these logical comparisons, they are expecting atomic information. So let's rewind. We're going to talk about this real quickly. Notice step 1 is always to get an atomic vector every single time. This is an atomic character vector. And then if it's character vector, we perform character operations or string operations, which is why it's str underscore for string detection. Back here, this was an integer vector. First run is an integer. And so we can perform arithmetic logical comparisons on this integer vector. But again, this is atomic. This doesn't really work if we're trying to go into a list. And here are some exercises here for you to play with this and try to understand how, yes, tibbles are lists, but this added structure, this added rectangular structure of having a fixed number of rows and a fixed number of columns allows us and enables us to do some really powerful logical statements on that we don't get when we just have lists. So we're going to pause the video again. And we're back, okay? So I hope that you worked through these exercises and you learned something and you understand a little bit why a lot of times when we're dealing with data, yes, under the hood, a tibble is a list, but most of the time we need that extra rectangular structure to help us corral and structure our data in a way that it's meaningful for us to do these comparisons and analyses. So now finally, I want to talk about named subsetting. So here, named subsetting, this is, we've seen it before where we type the quote symbols. We say, okay, give me single square brackets and then type quotes. There's another way to do this, okay? So yes, this works for lists, this works for tibbles, but the other way is with the $ operator. Now, I know I just scrolled past these exercises. So let me go back here, do these exercises. Do these exercises, okay? These exercises are important for you to understand how tibbles and lists, what is similar, find what is similar, find what is different, and kind of wrap your head around how R thinks about your data. Okay, it's very important that you understand how R is thinking about your data, because a lot of times you'll say, oh, I want to do this thing. I think my data is structured this one particular way. And you go to operate on that, you get an error or you get something very unexpected and you say, okay, well, that's not what I expected to get. It may be because the input to these functions or the input to this data analysis pipeline is different than what you thought. So if you were expecting to start with a certain type of data that would yield at the end a certain type of data, If you start with a type of data, if you think this is one type of data, but R says, no, it's not, then that means at the end of the pipeline, you're going to get something completely unexpected, or you're just going to get errors. So pay attention to this. And that's what these exercises are for. These exercises are to help build up that comfort, build up that experience in working with different kinds of data objects. So again, back to the $ operator. Now this operator we have not yet seen before. We've seen it referenced. Like, so when we printed, let me see over here. We see right here, when we look at the attributes, we see the $. So this is R telling us that this $ is important, but we so far hadn't worked with it. Okay. Now this is a list, as we mentioned before, the dim names attribute, it says it right here. It is a list. So lists, we can access the elements of the list using the $ operator. This is a special operator that only works on non-atomic vectors. So it works on tibbles, it works on lists. Okay. And here's how we get it. Okay. So if I take my ID vector and I say $max degree, I'm going to get the elements here. Notice though, this isn't a list anymore. This is an atomic character vector. Here, from the heroes data frame, I do $name. This is not a tibble. This is an atomic vector. Look at this. It's an atomic character vector. Okay. This is why the $ is so incredibly special here, because up to this point, we were using single subset operators, and that says, okay, give me the whole container, or we're using double subset operators, and we were trying to like get at the contents of this thing, where the $ just gives us directly what is the content. So you walk up to use our bakery example, you walk straight up to the counter and you say, put the cookie into my hand. That's the $ operator. Give me the cookie in my hand. Something else that we need to think about. Okay, so here's an exercise for you. You work on this. We'll pause the video here. Okay, so you worked on this exercise, and we're looking to see this function called pull, and comparing it to the single square bracket, the double square bracket, and also the $, and seeing how the similarities are there, and then also why might this function be useful. I'm going to give you a hint on this. The pull function might be useful if you needed to use if you needed to put it in a pipeline surrounded by pipe operators. But we will get more on. We'll talk more about pipe operators in the future lessons. But just put that in the back of your head that this might be useful if we have a pipeline of data analysis steps. Now, the other thing to notice here is that max degree is not in quotes. Okay, so if I go back to name subsetting up here, I've had to type single square bracket and then quote age or quote alias. Here, I don't have to. Okay, I'm typing something called a symbol object. Okay, now symbols are, if we go way back up to the front, there's this little tiny box that we haven't talked about so much in between. So everything in R is an object, and then vectors are these ordered collection of elements, and then functions are the verbs, the things that do. And then there's this little tiny box that I put in the middle called languages, and we haven't really talked about it. Okay, so languages are what allow R to connect functions to vectors. Okay, and I'm not going to go into a lot of detail with this. This can get pretty heavy duty, pretty advanced. But for now, understand that whenever we're working with the $ operator, you're going to type the name of an object as if that object were in the global environment. Okay, so just like if there's an object X in the global environment, you don't type quotes around the X. You just type X and it gives you back whatever the object is. The $ works a little bit like that, but it doesn't say go look in the global environment. It says look in this object, in this, whatever this list is. And remember, it only works for non-atomic vectors. So go into this tibble and get me an object called name, or go into this list and get me an object called max degrees. Um, so that's operating on the power of symbols, okay? So as a brief review, if I create an object called my integers and then specify, give me the mean of my integers, I didn't put it in quotes. I didn't say, give me quotes my integers. I am expecting that R knows how to interpret that this thing is an object. So the actual letters M, Y, capital I, N, T, E, NTGERS, I can't even spell today. That's not string information anymore. That's not a character string. This is a symbol representing the object in the global environment, that there's a container, there's an object in the global environment, and the label on the outside of the object is my integers. The contents of the object is the integer vector from 1 to 10. But R knows that when you type my integers as the argument to this function, like to give you the mean, that it is not supposed to find the average of the letters themselves, but to go into the environment that stores this thing and find that object, and bring it back to you and evaluate that object as this sequence of integers from 1 to 10. Okay? So we've already seen this before, especially with ggplot. So when we did ggplot data equals MPG, we didn't type quote MPG. We said just put in the symbol that represents the entire MPG data set. And then in the aesthetics function, we said, okay, let take the displacement information, the engine side information, out of the MPG data set, not out of the global environment, out of the MPG data set. How did it know to look for the displacement object out of the MPG dataset? It's because in the data layer, we specified the MPG object. So similar here, we're going to first specify the object. Say, go this, I'm giving you the heroes data frame, the heroes tibble, and I want you to go into the $, go into that object and get me this column. All right, so there's more exercises here. I want you to work through these exercises, learn the intricacies of the single subset operator, the single square bracket, the double square bracket, and the $, and get comfortable using these. Understand the strengths and weaknesses of each, okay? I want you to go through these exercises and work through this. And that is all for now. Next time, we're going to talk about importing data. So have a good one, and we will see you soon.